Hello, everyone, and welcome to another episode of WWT Experts. I'm your host, Matthew Coble, and today we'll be talking with WWT expert Mike DiVincenzo about segment routing. Mike has 25 years of experience working in networking, focusing on MPLS and segment routing and lots of different complex networking environments. Since joining Worldwide Technology in 2018 as a technical solutions architect, he's been working with our clients to expand the reach of both MPLS and segment routing in all of the industry verticals we serve. He's actively involved with the authors who define the standards for segment routing, and he's contributed to their books, 2 books on the topic, and the forthcoming book on SRv6. And if you're looking for a glossary of all of the different acronyms that go into networking, this is your guy right here. So Mike, welcome. Glad to have you with us today.
Thanks, Matt. Glad to be here.
Good. Well, listen, to start, just set the baseline here. So what is the current state of segment routing out in the marketplace today?
Okay, so first, let's just step back a little bit. So segment routing was conceived in 2012 by Clarence Fisfus. He's the author of Segment Routing at Cisco Systems. And the idea was to simplify things and to make things IP-centric instead of making them centered around traditional old classic technologies. So everything was rewritten from scratch. And currently, segment routing has gained a lot of steam over the last few years. When we talk about segment routing, most of the time you heard the term SR-MPLS, which is segment routing running over traditional MPLS data plane. And that has gained a lot of traction for a number of reasons. But the biggest reason of all is something called fast reroute. So from a technical term, we call it TILFA, Topology Independent Loop-Free Alternate. It's a fancy way of saying that a router on its own will individually calculate a backup path in case something fails, like the link to another router or an upstream router or a downstream router from that router, and it'll automatically reroute the traffic in what we say 15 milliseconds or less, which is acceptable for all video and voice traffic and real-time data. Up to now, that's been really hard to achieve. And to do that, we've had to use things like traditional classic RSVP-TE with fast reroute, which doesn't scale very well and has a lot of limitations and is extremely complex. Segment routing was built to simplify things. It was built to take the existing technology of MPLS and make it much simpler by removing protocols. So we remove the control plane protocols like LDP and RSVP, and we replace them just by using the existing IGPs, which you're probably familiar with, OSPF and ISS. And what we do is we encode the information we need for segment routing in the actual IGP. And we use the IGP to advertise all the information, but the data plane stays the same. So nothing changes. So what that means is that all your existing routers, all your existing hardware out there can support segment routing with just a code upgrade. So that makes for an easy transition, and it makes it so that it will be widely adopted.
So that's really getting just like some of that history of where this has come from and where we're getting to the current state with segment routing, which is great. But something else that is exciting in this space is traffic engineering becoming mainstream. So tell us what traffic engineering is, and why is that moving now into kind of common use?
Yeah, so great question. And traffic engineering is exactly what it says. It's engineering the traffic along a predetermined path, or a path different from what the IGP, like ISIS and OSPF, would choose as its default path. Now, in the past, the way we did that was something called RSVP-TE. RSVP stands for Resource Reservation Protocol. It was designed for many things, but it was adopted for traffic engineering. The problem with RSVP-TE is it's soft state protocol. So there's state all the time in the network, and it's very complex. And to do traffic engineering with RSVP requires you to plan the network out, especially from a fast reroute perspective. What segment routing traffic engineering brings to us is it simplifies that process dramatically. Again, we take all of that traffic engineering information and we transport it again in ISIS and OSPF. So we don't need another protocol like RSVP to transport this information. We also don't need a soft state. We encode the information as labels. When we're talking about SR-MPLS, we do it as labels. And we encode those labels at the source of the packet. And that source could be a router, or that source could be a host. As long as the host can encode the packet with the right labels, it sends it through the network. And then the other routers in the network, the other devices in the network, all they do is they look at the topmost label and they forward the packet along the network. And that's it. So we call that source-based routing, because we're not really looking or doing any state or keeping track of anything. All we're doing is taking an encoded path, putting it in the packet, and sending it along. But what SRTE does, especially with modern day SRTE with segment routing, is it offers a number of enhancements. So we've always routed the network based on the cost of the IGP. It means the bandwidth. The largest links is where we're going to send the traffic. We've also had something that was manually configured called a TE metric, which you could assign to an interface, and you could use that instead. And you could basically do like a manual implementation of like delay. But now what we do is we measure delay with something called performance monitoring. Apart from segment routing, we measure the delay with UDP probes. And then again, we transfer that information, or we advertise that information throughout the network in ISIS and OSPF. And now we can build a path that's based on delay, not just bandwidth. We can also mark certain links or nodes as something we don't want to traverse. And we use something called affinity. And when we do that, we now create a customized path that'll avoid a certain link. This is really desirable in situations where companies or organizations have tariff-based links, and you don't want to use that link except for backup. So you mark that link and the router will avoid that. We can also create paths through the network that are disjoint from the single head end or multiple head ends. And the way we do that with multiple head ends is we implement something called an SRPCE, which is a traffic engineering controller. That's Cisco's term for it, but basically everybody has it out there. And again, these terms are coined by Cisco because Cisco invented the technology. And this SRPCE will then direct the traffic along the path based on the information he knows. So he can actually program two different routers or two different source devices to never traverse the same path. You can't do that without a controller. So that's where the controller comes into play and has a lot of advantages. There's a lot more things we can talk about with SRTE, but that would be a very detailed discussion.
Yeah. Well, that's an excellent summary. And I want to back up a little bit to MPLS, right? Because that's been around for years and it's still very much in place. I wonder if you speak a little bit to what sparked the rise of MPLS and how does it still play a role in networks today?
Yeah, so MPLS has been around for a long time, like you said, since the late 90s. Again, a technology developed and invented by Cisco Systems. And the RSVPT was actually something deployed by Juniper to solve the traffic engineering solution. But this is something that's been around for a really long time. And the main birth of MPLS was twofold. It was to consolidate networks, that you could have one network that would transport your video, voice, and data all over the same transport network, whether it's an ISP providing it to you or whether it's an organization building their own MPLS network. And the other thing was to increase forwarding onto classic routers were slow. All of the packets had to go through what we call like a centralized CPU, similar to the CPU in your computer, your desktop. One CPU would do all the forwarding. So by taking the forwarding decisions and not making them be IP routing lookups and making them label forwarding, we could increase times and speed. No longer relevant in today's networks because today modern day routers have what we call layer 3 line cards. They do all the forwarding in ASICs on the line card, so you don't have to engage the centralized CPU except for pretty much the control plane. So packets are forwarded very fast. But we still have the advantages of where VPNs were born. VPNs were born from MPLS because you can segregate traffic by putting a label on a packet, and you can then have different traffic that is not seen by different organizations. And you can actually, as a service provider too, or even any organization, you can transport net traffic over the same network, and you can have overlapping IP address space because the label makes it unique through the network. And MPLS provides that layer 3 VPN, and then your layer 2 VPN became very popular. The ability to create a layer 2 network over a layer 3 network to make two devices look like they're directly attached, or multiple devices appear like they're on the same LAN. So that's where L2 VPNs came from. Like I mentioned before, the MPLS hasn't changed, so the data plane has not changed. We're still using the same exact data plane with SR-MPLS. We're just changing the control plane. We're making it less complex, and we're incorporating it into ISIS and OSPF, which is what makes it less complex. And it actually creates the advantage that you don't have to have the two protocols, these control plane MPLS protocols and the routing protocol in sync, because now the routing protocol is doing everything. So again, that makes things a lot better.
Well, so another newer component is traffic engineering controllers and bandwidth brokers, in particular, Cisco's Crosswork Network Controller. So can you tell us a little bit about how those work?
Yeah, so when we talk about controllers, there's two types. There's the traffic engineering controller, which is the SRPCE in Cisco terms. And that just runs something called PCE, which is a protocol that's been around, PCEP, for a really long time. And that's Path Computation Element Protocol. And basically, it's just devices communicating. So you got a controller communicating with routers, or a controller communicating with a server. And basically, the router or server requests the traffic engineering path from the controller. Why? Because the controller, again, can plan two paths from two different head ends. So two different head end routers can request this path, and they can make sure their path is disjoint. You can't do that without a controller. You can have disparate domains, meaning domains that don't have IP reachability between them, and you can forward traffic across them. You can scale much greater with SRPCE controllers, but then you come in with the bandwidth broker. And the bandwidth broker, like Crosswork Network Controller, often referred to as CNC, can do additional things that you can't do with just the PC alone. And how it does that is it gathers data from the routers. So it's connected to the routers, it's getting telemetry data, it's getting SNMP data from the routers, and it's using that to make intelligent decisions. For example, you could build a path that says, I don't want a path from point A to point B that traverses a link where the bandwidth on any given link is greater than 80%. And the router is monitoring those links all the time. Sorry, the controller, the bandwidth broker, is monitoring these, the CNC is monitoring these links all the time. And if a link becomes congested, he'll then reroute the path and make sure it doesn't traverse that link. You can also have it do things in real time, like have it monitor links. And if a link becomes, or a path becomes congested, any link along that path becomes congested, have the CNC or the Crosswork Network Controller or the bandwidth broker, or however you want to refer to it as, basically create a bunch of different paths that move traffic off of the current link and free up the congestion. So there's two examples of how you can use CNC. These things are going to grow and change over time, because as we start gathering more and more telemetry data and telemetry becomes more and more mainstream, we'll be able to make more intelligent decisions, and we'll have really what we refer to as true software-defined network.
Right, and that bridges into my next question for you, because really at this stage, segment routing is the foundation of complete software-defined networking. So what do you see as the current state-of-the-art in that software-defined networking space today?
So when we refer to software-defined networking, it's just a fancy buzzword term, but the only real SDN in my estimation or my opinion out there is SRv6. So SR-MPLS is trying to do some of the things that SRv6 does, but SRv6 takes segment routing v6 is what it stands for, to the next level. And what it does is it removes the MPLS data plane. And by removing the MPLS data plane, it now simplifies things even further. So now you have no MPLS anymore. And what are you going to use? You're going to use your IPv6 packet, and you're going to take your IPv6 address, and in the IPv6 address, you're going to encode labels into that. And you have something also built into the IPv6 RFC, which has routing extension headers. And you can then have multiple labels within the packet, and you can encode them all in an IPv6 packet. So what that means is any device along the path that's running IPv6 becomes an SRv6 transport router because it's just an IPv6 packet. And he's forwarding the packet like that without even knowing. But what we really get with SRv6 when you look at the RFC is we get a whole bunch of encoded, I would say, like small network programs. These are ways we can encode in an IPv6 packet what we want to do with the packet. And we're not limited to just routers. The Linux kernel for many years has supported, that's over 5 years now, I think, has supported SRv6. So any device running SRv6, whether it's a firewall, a deep packet inspector, whether it's something like Snort, which supports SRv6, you can then encode in the packet. Not only do you want to forward the packet from point A to point B, but you want to forward it from point A to point B, and you want it to traverse certain devices, like a firewall, like a deep packet inspector, before it gets to its end destination. So now you're really seeing true software-defined networking in action, and that does exist in today's current implementation of SRv6. So SRv6 really is, in my estimation, the next generation of networking as we move forward.
Cool. Well, listen, I'm going to go off script just a little bit, but for those who are listening in today, I'm curious if you think about sort of segment routing and then software-defined networking as you just described. And organizations are really thinking about that and how they can implement that. What are the top 3 things you would encourage people to keep in mind as they are moving forward with these technologies?
So with SR-MPLS, it's really quite easy because what you have is an existing MPLS network. So long as you can implement MPLS, and that's easy to do, any network out there today can implement MPLS. And if a router can't, it's just because it's not running the code that supports MPLS. So it's a code upgrade as a minimum. So that makes it really easy when you're doing SR-MPLS. When you're doing SRv6, you need to make sure your network is ready for IPv6. There was a real craze for IPv6 around 2007. Everybody said it was, was going to take over the world. And unfortunately, people were slow to adopt it. Service providers rolled it all out. And it's rolling out, especially cellular providers. They all use IPv6 prevalently throughout their network. But a lot of people have deployed it or haven't deployed it at all, or if they deployed it, they don't use it that much. So getting your network ready for IPv6 is going to make it so in the future, you'll be able to implement SRv6. A lot of people are adopting SR-MPLS. Some people are adopting SRv6, not as many, and that's understandably so, because the migration path from MPLS to SR-MPLS is nothing. And migration path to SRv6 is a little bit more entailed. So of course, you're going to see people adopt SR-MPLS initially. And SR-MPLS has been around for quite a bit longer than SRv6. So it's more mature. And all your vendors are very well, all their code is very mature, where SRv6 is not quite at state. Cisco is definitely still ahead of the game and the crowd in SRv6. But it's definitely the future, and to prepare for it, you want to make sure your network is IPv6 ready. Otherwise, there's really nothing else you really need to do. That's the beauty of segment routing, that it's such an easy migration path. And when you want to implement things like fast reroute, which is the single biggest reason when people are polled why they want to implement SR-MPLS, it's topology independent loop-free alternate, or TILFA, or for short, just fast reroute. They want fast reroute support. And you can incrementally deploy it one router at a time because it's only dependent on the router's own, what we call shortest path database, like the ISIS or OSPF database. So it can be incrementally deployed one router at a time, which makes it really easy to deploy. That is the single biggest reason we see people deploying SR-MPLS. But I do believe SRv6 is the future.
All right, well, that gets us to our last question, Mike. Always love to ask our experts where they see things going in the future. So as you look at the future of segment routing, what are you excited to see coming up in the next, say 2 to 5 years?
Yeah, so I would like to see more people adopt SRv6. Again, IPv6 has been the limiting factor because people are still a little hesitant and not that comfortable with IPv6. But once they do, and once they see how powerful SRv6 is, You can actually do SRv6 over the public internet. You'd probably want to encrypt your packets, but you could theoretically do a layer 3 VPN over the public internet because the public internet is an IPv6 network. And the only routers that need to be running SRv6 code to do SRv6 end-to-end across two what we call, like say, PE or provider edge routers running the layer 3 VPN is those routers itself. So if you have two routers doing layer 3 VPNs, they need to run SRv6. Everybody else can run IPv6. And if you have SRv6 deployed in, say, either a national network, international network throughout the globe, whatever it might be, and you have different spots across the way or different locations along the way that have SRv6 nodes, you can forward traffic to that node and then to another node. So you can now engineer your traffic across the public internet. So there is an option to run SRv6 in combination with SD-WAN. And because SD-WAN is still limited to what the public internet path is, you can't change that, but SRv6 can. If you've got nodes throughout the network. So that's what I'm really excited to see. The use of SRv6 in the public internet to do these kind of things, and the use of SRv6 to demonstrate, not to demonstrate, but actually to implement the true software-defined networking with devices and hosts out there. So a host out there that's making a request of, like we talked about before, like a traffic engineering controller or a bandwidth broker, programming a host and telling the host, send the packet via SRv6 end-to-end across the network. And by the way, avoid this link, take the low delay path. One path should be the high bandwidth path. Another, some traffic should go over the low delay path. Avoid a particular set of links. Do all these types of fancy things you can do with segment routing traffic engineering, which people never did before because it was just too complicated. And now it's really attractive to do SRTE itself over any transport network because we've made it, honestly, so easy to do.
Well, Mike, I gotta believe that given your deep expertise, you have one of the most sophisticated home networks on the East Coast of the United States, probably, right? Thanks so much. No?
No, simple router. My Hi-Fi system is complicated, but not my network. I keep it simple because that's all I need.
Very good. Well, listen, very much appreciate you being with us here today. So thanks so much for joining us.
Thanks for having me, Matt.
Yeah, very good. And thank you for coming as well. Another great WWT Experts session. We've got plenty more coming up in the future and a great back catalog on wwt.com/events. Go check those out and we'll see you next time. Thanks for coming.